Okay, hello all, and welcome to the section 10.2 video lecture. So let's go ahead and get started by opening up our note sheets and opening to section 10.2. So as I said in the last video, you can find these handouts on my Math Lab under the Handouts tab. If you'd like to print some off or put them on an iPad or something like that to be able to follow along and take notes along with me. So last time we talked about the language of hypothesis testing and basically all the stuff that's going to go on with hypothesis testing except doing the actual test. So that's what we're going to talk about today is how to actually do a hypothesis test. So when observed results are unlikely under the assumption that the null hypothesis is true, we say the result is statistically significant. When the results are found to be statistically significant, we reject the null hypothesis. Now, as we go through this section, you're going to notice some references to the classical approach. There are two methods for doing these, and the classical approach used to be the most common way to do it, but now pretty much everybody uses the p-value approach to do these. And considering we're online and things are already a little bit more difficult, I'm just going to stick to the easier one and the more common one, which is the p-value approach. So anywhere in these notes you see the classical approach method mentioned, you can should just be able to ignore that. So assuming that h naught is true, if the idea behind the p-value approach is assuming that h naught is true if the probability of getting a sample mean as extreme or more extreme than the one obtained is small, we reject the null hypothesis. So the idea here is we're going to find the probability of getting the sample we got or more extreme, farther from the mean. And then if that probability is low, we're going to reject the null hypothesis. So to do a hypothesis regarding the population proportion, we can use the following steps provided that these things are true. The sample is obtained by simple random sampling. N times p times 1 minus p is greater than or equal to 10. Remember, if this is the case, then the distribution of p hat is approximately normal. We learned about that in chapter 8 and then used it in chapter 9 as well. And the samples have to be independent of each other. And in order for the sample values to be independent, what we want is the sample size, lowercase n, to be less than or equal to 0.05 times capital N. So that means less than 5% of the population. And in most cases, when our population is things like all adult Americans or all teenagers, that's not going to be that hard to do because 5% of all adult Americans would be something like 5 million people, and our sample sizes are going to be nowhere near that. So if those things are true, then we can do the following steps. Step 1 is determine the null and alternative hypotheses. These hypotheses can be structured in one of 3 ways, and notice there is a typo in all of these. Wherever it says mu here, it should say p. I've never gotten around to fixing this, but the idea here was these are from, I copied and pasted from the next section when I originally made these, and that gave me these mu's. So after you do this, before you do any testing of any kind, you want to select your level of significance alpha, depending on the seriousness of making a type 1 error. Remember, if it's a big problem, if you reject the null hypothesis when it's actually true, you want to choose a very small value for your type 1 error. So then you can compute the test statistic, which really just means find the z-score for your data value. So that's going to be z naught is going to be p hat minus p over the square root of p times 1 minus p over n. And then you can use a table 5 to determine the p-value. We're actually going to use ClassCalc to do this. And if the p-value is less than alpha, then we reject the null hypothesis. If it's not less than alpha, we do not reject the null hypothesis. And either way, we state the appropriate conclusion, just like we learned to do in section 10.1. So I'm going to go and skip over this problem on page 9, just for time's sake in the video. And we're going to go and go into the real application ones here. So we're not going to use these steps. These are for a TID 3 or 4. If you have one at home, feel free to use it, to use this. But instead, right, we're going to use ClassCalc. Okay, so let's look at where that is in ClassCalc before we get into the problems here. So if I click on my ClassCalc and I'm in the graphing function like this, I'm just going to clear out what I was working on with calculus the other day. And we're going to go to stat. We're going to go to test because we're doing a hypothesis test. And then for this, we're dealing with one proportions and z-test. So we did one prop z-int when we were doing confident intervals for proportion. So to do this for hypothesis test, we're going to choose one prop z-test. And then notice, to do a one prop z-test, we need to input 3 things: p naught, x, and n. Okay, so in our ClassCalc, we're going to do one prop z-test. And we do that, it's going to do one prop z-test, and we're going to enter our p naught, our x, and our n. And our p naught is from the hypotheses. So from hypothesis. Okay, so let's try a problem with this. So in August of 2003, 56% of employed adult Americans in the United States reported that basic mathematical skills were critical or very important to their job. The supervisor of the job placement office at a 4-year college thinks this percentage has increased due to increased use of technology in the workplace. He takes a random sample of 480 employed adults and finds that 297 of them feel that basic math skills are critical or very important to their job. Is there sufficient evidence to conclude that the percentage of employed adults who feel basic mathematical skills are critical or very important to their job has increased at the alpha equals 0.05 level of significance? Okay, so the first thing you want to do here is you want to check and make sure you can do this. So the first question, remember the things that have to be true to do this is you have to get your data from simple random sampling. N times p times 1 minus p has to be greater than or equal to 10. And our sample values have to be independent. So first things first is this did come from a simple random sample, right? He got a random sample of 480 employed adults. So then we want to take n, which in this case is the sample size, 480, times p naught, which is going to be 0.56, 56%, times 1 minus 0.56. And see what we get for that. So in my statistical calculator, scientific calculator, I'll take 480 times 0.56 times 1 minus 0.56. And for that, we get 118. And 118 is definitely greater than or equal to 10, so that works. And then, do you think 480 employed adults is less than 5% of the total number of employed adults in America? Yeah, it definitely is. For example, this past week, due to COVID-19, the number of people who signed up for unemployment was 6 million. 5% of that would have been about 300,000, which is a lot more than this. And there are more employed Americans than unemployed Americans, so this is definitely less than 5%. So these values are independent. So now we can do our hypothesis test. So step 1 of that is write our hypotheses. So H naught is always either mu or p equals the value. In this case, p equals 0.56. And then our alternative hypothesis is he thinks this percentage has gone up. It's increased. So that's why we're going to choose p is greater than 0.56. And so then we can enter our values into our calculator. So that means we're going to do a 1 prop z-test. So 1 prop z-test. And we're going to enter our p naught, our x, and our n. So our p naught is 0.56. Our x is 297. and our n is 480. Okay, so let's go back to our calculator and do that. So we go to graphing calculator, stat, tests, one prop z test, put in our p, which is 0.56, our x, which was, sorry, I forgot what our x was, 297, and our n, which is 480. And notice it actually gives us all the things we probably could want for this. We've got the z, so that's the test statistic. So the test statistic here would be 2.593. And then it gives us our p-values in all three directions. So we've got, if we were doing less than, it would be 0.9952. If we're doing greater than, it's 0.00475667. And if it was not equal to, it would be 0.0095. So you just have to pick the right one. And the right one here is greater than, right? We're doing p greater than. So our p-value is 0.0048. Okay, so from this test, we get p equals 0.0048. And the question is that less than alpha? Well, our alpha is 0.05, so in this case, yes, it is less than alpha. So because 0.048 is less than 0.05, we can reject H naught, and then we can state a conclusion about the alternative hypothesis, just like we did in the last section. So we could say there, and we rejected H naught, so there is sufficient evidence to suggest the proportion of adults who believe math is important to their job has increased. Okay, and so that's the idea. So we did the hypothesis testing and the rejecting and the conclusion in the last section. And so now we're just talking about how do we use statistics to find out should we reject H naught or not. So that's the new part here. Okay, so let's go ahead and try a second one together. So the second one says, in 1994, 52% of parents of children in high school felt it was a serious problem that the high school students were not being taught enough math and science. A recent survey found that 256 of 800 parents of children in high school felt it was a serious problem that high school students were not being taught enough math and science. Do parents feel differently today than they did in 1994? Okay, so I'm going to skip over the first step here because 800 times 0.52 times 1 minus 0.52 is definitely going to be greater than or equal to 10. So we should be good to do a hypothesis test. So let's go ahead and write our hypotheses. So the first one is always that we equal whatever the value was. So in this case, p equals 0.52. And the alternative hypothesis here is that we no longer eat that, right? Because they feel differently today. So feeling differently means it's changed, so that's not equal to 0.52. And so then we're going to do a one prop z test, and we're going to put in our p, which is 0.52, our x, which is 256, and our n, which is 800. Okay, so I can even use the same one here if I want. Just delete what we had in there. So 0.52, x is 256, and then n is 800. I feel like there's probably a typo in this problem, but we can go ahead and use the value. So in this case, we're looking for not equal to. So the probability of being not equal to, it says here, is 0. So p equals 0. So the question is that less than 0.05? And the answer is yes, it is. So we can reject H naught and say there is sufficient evidence to suggest, and now I'm going to shorthand this a little bit just for time, but you would want to write out in detail the conclusion here, which would be there is sufficient evidence to suggest that the proportion of parents who think their children are not being taught enough math and science is different today. And so what I'm going to write is to suggest the proportion is different. But if you're writing out a nice, good conclusion, you'd want to include more detail than that. Okay. So what I'd like y'all to do is flip over to the next page, pause the video for a moment, and try these two problems. Okay? And then we'll go over them together, and then we'll move on to the next page. Okay, so now that you've had a chance to try these, let's go through them together. So the first one says, in February 2008, the Gallup organization surveyed 1,034 adults between 30 and 64 years of age and found that 548 were worried that they will outlive their money after they retire. Does the sample evidence suggest that a majority of 30 to 64-year-olds in the United States are worried that they will outlive their money? Okay, so this one's a little trickier because they don't give you the percentage outright. The key word here is a majority. And so what does a majority mean? Well, a majority means more than half. So our null hypothesis would be equal to 0.5. An alternative hypothesis would be that it's greater than 0.5. Because if more than 0.5 of the population feels this way, then that would be a majority. Okay? But now we can still use one prop z test. Our p naught is 0.5. Our x is 548. And our n is 1,034. Okay? So now we can put that in our calculator. So 0.5, comma, 548, comma, 1,034. And so in this case, our greater than is 0.269, 0.0269. So our p-value for greater than is 0.0269. So that is less than alpha. So we can reject h naught and say there is sufficient evidence to suggest that a majority of Americans are worried that they will outlive their retirement. Okay? And I just put ... to shorthand it here in the notes. Okay? And then the second one, it says in 2000, 58% of females aged 15 years of age and older lived alone. According to the U.S. Census Bureau, a sociologist tests whether their percentage is different today by conducting a random sample of 500 females aged 15 years of age and older and finds that 285 are living alone. Is there sufficient evidence at the alpha equals 0.01 level of significance to conclude that the proportion has changed since 2000? Okay, so H naught is that P equals 0.58. H1, we want to know what's the, we're testing that it has changed, so that would be P does not equal 0.58. So we're going to do one prop Z test of 0.58, comma, 285, comma, 500. .58. And then 285 out of 500. And so we get that the not equal to proportion here is the one we want. So that's 0.6505. So P equals 0.6505, which is not less than P. Not P, not less than alpha. So that means we do not reject H naught. And since we don't reject H naught, that means there is not sufficient evidence to suggest the proportion of females aged 15 years of age or older living alone has changed since 2000. Okay, so that's the idea of how we can use this one prop z test to do hypothesis testing. Now, there are some other options. In a case like the one we just did, we could actually use a confidence interval to do this hypothesis test. So when we have a two-tailed test, a test where we're doing not equal to, one option is to use confidence intervals. So when testing P equals P naught versus P does not equal P naught, if alpha 1 minus alpha times 100% confidence interval contains P naught, we do not reject the null hypothesis. However, if the confidence interval does not contain P naught, we conclude that we do reject. So if you remember back to chapter 10, one of the things we talked about was the idea that if a sample did not include the population in its confidence interval, then we can conclude that the the population has changed. And that's the idea here, is that if we find a sample and the value we expect to be in that sample, the population value is not in our confidence interval, then things have probably changed. So as an example here, in June 2007, study conducted by Students Against Destructive Decisions, SAD, revealed that 37% of teens 16 to 17 years of age text while driving. Does a 2009 study by Princeton Survey Research Associates International, which found that 272 of 800 randomly selected 16 to 17-year-olds had texted while driving, provide evidence that the proportion of teens who have texted while driving has changed since 2007. Okay, so we start out by writing our null and alternative hypothesis, just like before. So in this case, P starts out at 0.37, and we want to know, has it changed? So that's P does not equal 0.37. And so now, because we're doing a not equal to hypothesis test, we can use a confidence interval. So if instead of doing one prop z test, I'm instead going to do one prop z int, like we did in chapter 9. So I go to my calculator. Let's hit enter. I'm going to leave that there for a second. I hit stat, test, and now I choose one prop z interval. And now I put in my x, my n, and my c level. So in this case, my x is 272, my n is 800, my sample size, and my c level is simply whatever alpha value we want to use. So in this case, it doesn't give us a value, so let's just go and use, at least I don't see it. So let's just go and use alpha equals 0.05 because that's the most common. So that would be 95%. 1 minus 0.05 is 0.95. Okay, so I go to my calculator, I put in 272. I put in 800. And I put in my confidence level, which is 0.95. And so I get a confidence interval of 0.307 to 0.373. And so the question is P in this interval? And the answer is yes. 0.37 is in the interval. So given P of 0.37, 272 to 800 is a sample we would expect because our population is in there. So that means we do not reject H naught. And so there is not sufficient evidence to suggest ... that the proportion of 16 or 17-year-olds who text while driving has changed since 2007. Okay, so that's the idea. And if we did this with a one prop z test, which is why I left this open up here, we should get the same result. So I put in 0.37 for P naught, 272 for X, and 800 for N. Notice that when we do the change one, we get 0.0788, which is greater than 0.05. Therefore, we would not reject the null hypothesis. So you get the same final answer either way, but there are two different ways to do these not equal to confidence intervals. So why don't you pause the video at this point and go and try the second one. Okay, so let's go ahead. Now you've tried it, let's go through it together. So according to menstuff.org, 22% of married men have strayed at least once during their married lives. A survey of 800 married men results in 122 indicating that they have strayed at least once during their married life. Construct a 95% confidence interval for the population proportion of men who have strayed. Use this interval to assess the accuracy of the statement made by menstuff.org. So, H0 is going to be P equals 0.22. H1 is going to be, we're seeing if it's changed, so P does not equal 0.22. So we can make a 1 prop Z int using our sample data, which is 122 out of 500 at a 95% confidence level. And when we do that, so 122 out of 500 at 0.95, and we get 0.206 to 0.281. And so is our confidence, is this value in our interval? And the answer to that is yes, it is in our interval. Okay, so we do not reject H0. And we can say there is not sufficient evidence to suggest that the proportion of married men who are straight is different than 22%. Okay. So then the one last thing that's in this section is this is what we do if n times p times 1 minus p is greater than or equal to 10. But what if that doesn't happen? So let's look at that now. So on the next page, it says test hypotheses about a population proportion using the binomial probability distribution if n times p times 1 minus p is less than 10. Okay, so for a right-tailed test, that's going to be the probability that x is greater than or equal to p hat. Okay, and for this one, it'll be the probability that p hat is less than or equal to x. Whoops, nope. This would be the probability that x is less than or equal to p hat. Okay. So if the p-value is less than the level of significance, then we reject the null hypothesis. So let's go ahead and take a look at this. So according to the U.S. Census Bureau, in 2000, 9.6% of Californians had a travel time to work of more than 60 minutes. An urban economist believes that the percentage of Californians who have a travel time to work of more than 60 minutes has increased since then. She randomly selects 80 working Californians and finds that 13 of them have a travel time to work that is more than 60 minutes. Test the urban economist's belief that at the alpha equals 0.1 level of significance. Okay. So our null hypothesis here is that p equals 0.096, and our alternative hypothesis is she thinks it's increased, so that's p is greater than 0.096. However, when we try to take n, which is 80, times 0.096 times 1 minus 0.096, we get we get 3.072, which is not greater than or equal to 10. So we can't use our one prop z-test. But what you should notice here is we've got a p-value, which is 0.096. We've got an x value, which is 13. And we've got an n value, which is 80. And those are all the things we need to do a binomial probability distribution. So if I go into my calculator and go to the graphing function, and we go to stat, and we do a distribution or plot, and we can do a binomial distribution. And this is what we did back in chapter 6. So you enter your n, which is 80, and our p, which is 0.096, and we get this binomial probability distribution. So now what we want to know is, what's the probability of getting more greater than or equal to our sample size? So we hit CDF, and we put in our x, so that's 13. And so we get a probability of 0.0410. So we get a p-value of 0.0410. And so is that less than our alpha? And the answer to that is yes. So therefore we can reject H naught, and we can say that there is sufficient evidence to suggest that the proportion of Californians whose commute time to work is more than 60 minutes has increased. Okay? And so that's how you can use binomial probability distribution to do these hypothesis tests. So why don't you go pause the video for a second and see if you can do these other two. Okay, so now that we've tried these, let's go ahead and go through these two together. So according to the U.S. Census Bureau in 2000, 1.5% of males living in Colorado were teachers. A researcher believes that this percentage has decreased since then. She randomly selects 500 males living in Colorado and finds that 3 of them are teachers. Test the researcher's belief at the alpha equals 0.1 level of significance. So H naught is that P equals 0.015, and H1 would be that P is less than 0.015 because the researcher thinks this has decreased, right, since then. And now, if we do n times p times 1 minus p, we're going to get something that is not greater than or equal to 10. So we can do the binomial probability distribution with x equal to 3 and n equal to 500 and p equal to 0.05. So I go into my binomial distribution and I change these to match our current problem. So n of 500 and a p of 0.015. Okay, and then we want to know what is the probability of getting 3 or less. Whoops, sorry. So we want x to be less than or equal to 3, right? Whoops, it's still not working right. There we go. And we get 0.0578. And is that less than alpha? Yes, because alpha in this case is 0.1. So we could reject H naught and say there is sufficient evidence to suggest that the proportion of adult males living in Colorado who are teachers has decreased. Okay. And then the last one says, according to the U.S. Census Bureau in 2000, 3.2% of Americans worked at home. An economist believes that percentage of Americans working at home has increased since then. He randomly selects 150 working Americans and finds that 8 of them work from home. Do a higher proportion of Americans work at home? Okay. So our H naught is that P equals 0.032. Our H1 is that P is greater than 0.032. And our X is 8. Our N is 150. So we can use the binomial probability distribution to do this. We put in our sample size, which is 150. Our p-value, which is 0.032. And we want to know what is the probability that we get 8 or less. Okay, so that x is less than or equal to 8. So I put in 8, and we get 0.947. Oh, whoops, sorry, we're trying to increase. So we put in 8, and we get 0.1010. I mean, sorry, that's not correct. If I round to 4 decimal places, I get 0.1099. Okay, so P equals 0.1099. That is not less than or equal to alpha. Not less than alpha. So therefore, we do not reject H naught. And we cannot say there is not sufficient evidence to suggest that the proportion of Americans working from home has increased. Okay, so that's it for section 10.2. This stuff at the end we're only going to use if we have very small sample sizes or if the p-value is very small. Otherwise, you can use one prop z test. So don't forget to do the homework. If you have any questions, feel free to email, text, or call me. And then next time we will talk about doing the same thing, but for the population mean.